Good morning, everybody. Time for another exciting morning of organic chemistry with your host, Dr. White. And this lecture is produced and directed by Dr. White. All right. Got a lot to do and hopefully enough time to do it. If you didn't check your email, you should, because I sent this out yesterday. A week from tomorrow will be test number 1. Test number 1 is on Thursday the 16th, and we'll have 10 pages. There are 14 problems. Some of the problems have multiple parts like A, B, C, and D. There'll never be a multiple choice question on my test. ACS I have no control over. We'll cover alkanes, cycloalkanes, alkenes, alkynes, and aromatic compounds. The point breakdown for test number 1. 13 points, general knowledge, like 20 bonds to carbon, I call that general knowledge. And 45 points, nomenclature, 2 types of nomenclature questions. Here's the structure, give the IUPAC name. The other one is, here's the name, draw the structure. And finally, 47 points on reactions. All but one problem of the reactions will be give the organic or give the product or products for the following. The one that exception will be give the starting material or materials for the following. If you notice, it adds up to 105 because there's 5 bonus points. I do not designate this problem as a bonus point problem. I just have the whole test add up to 105. You pick which 5 points you want to call bonus. What that means is, when I calculated the total points to get your percentage, I use 100 to get 632, I think it is, or 630, whatever it is, in my syllabus. But for the test, you can get 105, and I've had students who get more than 100% of the total for their grade. Amazing students, and hopefully all are here amazing students. Actually, I'd like to thank you. These are going really good. I'm really having a good time, and I hope you are too. If you have any questions, feel free to ask. And one of your colleagues sent me an email. Is this a time test? All tests I give and all tests I've ever taken are time tests. You'll have the whole lecture period from 10 o'clock. I start promptly at the top of the hour, so be here on time. If you come here late, you do not get extra time. And we'll end roughly 10:50 and do the lecture. Any questions? As I said before, my tests are written, so if you've done the practice problems, you know the material, you should be done in about 35-40 minutes, it'll usually take. If you haven't done that, what do you all day? That wouldn't help. So do the practice problem. It will help. Any questions on test number 1? All right. Yesterday I was talking about aromatic compounds. Speaking about compounds in general knowledge, anybody drive by a gas station and think of alkanes? Well, this is a tough group. I will not give up easily. When you leave the classroom, organic chemistry is all around you. You see a candle, think of alkanes. If you see baby oil or Vaseline, think of alkanes. Do you happen to think of aromatic compounds if you smell something like cinnamon or vanilla? Think about it. That's all around your life. Well, yesterday I talked about aromatic compounds. We're going through the naming, the starting. The most important are the simplest aromatic compounds, 6 carbons, 3 double bonds, is called benzene. IUPAC in their infinite wisdom, and I truly mean this, that for eons now people have been calling this molecule benzene. We're not going to change them, so let's make it the IUPAC name. Do not, on test number 1, if I were to put that down and say, give the IUPAC name, students sometimes put down cyclohexatriene, which is wrong. Tri, 3 double bonds, no, it's benzene. If you put a methyl group on benzene, what do we call that? Toluene. It's not called methylbenzene because, again, I knew this molecule somehow got the name toluene. I have no idea how it got the name toluene, just like I have no idea how this is called a door, even though I do know it comes from German, which in German is Tor, is door, and I think that's how, and about knowing my German, Mach the Tor, close the door. But anyways, back to organic chemistry, this is toluene. And methyl group on benzene ring, toluene. Remember, if I were to write on the test, draw the structure, by the way, after you take test number 1, you'll understand why I do that. If you haven't figured it out yet. But anyways, draw the structure of benzene. And if you do this, and I put a 0 there, and you come to me after the test and say, shouldn't I get partial credit? And I'll say, no, that's cyclohexene. Benzene has 3 conjugated double bonds. You can draw it that way. You can draw it this way, which is the other resonance structure. Or you can use, these are the Kekula structures, which I just think are cool, or it's totally acceptable to draw it that way. If you don't put the stuff, the double bonds or the circle showing the pi cloud inside, that's not benzene, it's cyclohexane, and I'll mark it wrong. Common mistake on test 1. I'm telling you this so you don't make it. Please don't. Now, I will never ask on a test, but we'll talk about it more, and I mentioned it yesterday. When you have a vinyl group on a benzene ring, that's been called for eon styrene, and the common name became the IUPAC name. It's not vinyl benzene. I have heard some people call it that, but I won't put that on the test. All right, numbers are used just like on a cyclohexane ring, but I'm going to skip this slide real quick. I'm just come back to this because I want to go to this slide. I'm on slide 14 for those of you who have printed out the slides. For those of you who don't, it's right here on the board. All right. There are other substituents that also can be used with alkanes and cycloalkanes and double bonds that I haven't mentioned because I really wasn't going to talk about them until I came to now aromatic compounds. So let's talk about it. If you have a chlorine on a benzene ring, we call that a chloro group. If you have a bromine on a benzene ring, or it could be an alkane too, we call that a bromo group. Iodine is called iodo, and fluorine is called fluoro. You take the name of the element of the halogen, drop the I at the ending like chlorine, and replace it with an O. So the question would be, what's the IUPAC name for this? Well, what's the substituent? Chlorine atom. Chlorine is called a chloro group. Since it's on a ring, just like you learned with cyclohexane, when there's only one substituent on a ring, you use no number. And then, what is this? Ring, 6 carbons with 3 conjugated double bonds, benzene, and I'm done. Chlorobenzene. Why don't you try this one? What's the IUPAC name for that? And after yesterday's lab, and also after tomorrow's lab, I'm learning names to look out. You'll no longer be anonymous students in my class, which I think is a good thing. All right, let's take a look at this. Ooh, what's different? Always look at a molecule. I've got a ring with 3 double bonds. Ooh, I've got a halogen bromine. How do we name bromine? Bromo. And then I have my ring, benzene. And I have bromobenzene. Now, there are 2 other substituents. One I like you to know, hint. The other I won't ask on ever on a test. The one you should know, nitro group. Nitro is NO2, and it turns out nitro groups have an important role in aromatic compounds, which I'll talk about. Very important. And the bond from the benzene ring is to the nitrogen. The 2 oxygens are bonded to the nitrogen also. And this is called nitrobenzene. Again, 1 substituent, no number. Nitro group, NO2. Now, a group that I will not ask you to learn, but I'll talk about later when we get into detergents, and we'll do a reaction also in aromatic compounds. This is called sulfonic or sulfonic acid group. And by being able to put this on a benzene ring and doing another modification of the sulfonic acid in the benzene ring, modern organic chemists, by the end of World War II, in the late 1940s, were able to make a specific special molecule that you all use. And that's the molecule in detergents that gets your clothes clean. So if you're ever wondering, why am I learning this stuff? Well, it gets pretty basic. If you like using detergent to clean your clothes in your washing machine, as opposed to using bar soap or something like that, it's due to be able to put a sulfonic acid group on there. That reminds me of this interesting story. A company I was working at was using another company to make some products for us that we needed to use. It's called toll producing. How that got that name, I don't know. And when you do that, part of my job was to, in the areas I was responsible for, go to the company and inspect them. And the company made sulfonic acids, which are quite hazardous, like hydrochloric and sulfuric. I had to go there in the summer to Alabama. I think it was Birmingham. And it was right before 2000. It was the summer before 2000, 1999. And I remember they took me out to lunch afterward. They were doing a good job, and I was happy, and they were happy. I was happy because we were giving them a lot of business, millions of dollars. And I'm driving along, and I realized I'm in redneck country. How did I know that? There was a big billboard. I wish I had a camera at the time, but I didn't. That said, Y2K gun show. For those of you who don't remember Y2K, coming up 2000, people were afraid all computers would stop and all electricity and everything would be the end of the world. Here that you could tell Y2K gun show. Get your guns and be ready for Y2K. Whenever I see sulfonic group, I think of that. All right, let's back up. Now, it turns out for many eons, the special names have been evolved when you have only 2 groups on an aromatic ring. This does not apply to cyclohexane. Somehow it applies only to aromatic rings. Don't write that down. Let me use this bigger board. This will be a better job of explaining it. I have 3 isomers here. Isomers mean they have the same number of atoms, same type of atoms. And the first one, notice I have an ethyl group and propyl. It's on a benzene ring. So this would be ethyl N-propyl benzene. Next one, same thing, ethyl, N-propyl benzene. And finally, the last one, also ethyl, N-propyl benzene. Now, if we look at the first ring, first of all, I'll give you a chance to catch up. Tonight at midnight, I'll be giving speed writing lessons or structure writing lessons. All right, looks like the last hydrogens has gone down. Let's look at the first one. Notice that if I call one of the carbons that's on 1, this would be on 2. On this one, if I call one of them, it doesn't matter which one is relative. This is 1,3 disubstituted, and this would be 1,4. Well, it turns out somehow, and I've never found out how, but organic chemists eons ago came up with a naming nomenclature that for disubstituted aromatic, or mainly aromatic compounds, if we have one, 2 is called ortho. 1,3 is called meta. And 1,4 is called para. How they came up with that, I have no idea. But it's in use and still in use. Therefore, notice this is 1,2 disubstituted. I'll give you a chance to catch up. I guess I could have said mustard, but that doesn't make sense. Look out, it's evolving into bad humor Wednesday. All right, if you have 1,2 disubstituted aromatic compounds, only for benzene and aromatic compounds, this is called ortho. Therefore, this is orthoethyl N-propyl benzene. 1,3 is called meta. Therefore, this is meta-ethyl N-propyl benzene. And notice 1,4 is called para. So this would be para ethyl N-propyl benzene. And I would like you to learn these because if you use the numbers, I'm going to mark it wrong because everybody uses ortho, meta, and para. Nobody uses the numbers. So let's take a look at an example. And the question would be, give the IUPAC name for the following. And you look at that and say, what do? I look for something different. A ring with 3 double bonds conjugated. Conjugated means alternating. And I also have an ethyl group and I have a bromine. Notice this is 1, 2, 3 disubstituted. And oh look, someone put a nice table on the board for us to use. And 1, 3 is meta. First of all, it's a benzene ring. I have bromo and ethyl. And 1, 3, I'm going to put it up here because I'm running out of room. would be meta. So this would be meta-bromoethylbenzene. And that's how you use ortho, meta, and para. Anybody ever hear of the drug company called Ortho? I wonder where they got their name. You'll find out a lot of chemical and drug companies and other companies get their names from organic chemistry. Now, let me show you something important concerning toluene. What is toluene? Methyl group on a benzene ring. And this methyl group, when you're using nomenclature, is considered a substituent, even though it's included in the name toluene. So this is di-substituted. And therefore, if I look at this, base name toluene. I have a nitro group. Notice this is 1, 2, 3, 4. Methyl group on toluene is always considered number 1, and therefore I have 1,4 disubstituted. What is 1,4? Oh look, this nice table's on the board here, and it's para. So this would be para-nitro-toluene. And that's an important thing to remember. I would ask you, what's the organic, the IUPAC name for the following organic molecule? And being the nice person I am, I'll put this table up to help you out. And I also, somebody put this nice table up here to help you out. See how nice it is to be in my class? Oh, that was lame. All right, let's take a look at this, but before I go through the name, time for a public service announcement from me, Dr. White. Tomorrow I'll be going through the problem set on alkenes and alkynes, double bonds, triple bonds. I'd highly recommend you try them before I do them in class. That will help you on test number 1. All right, let's take a look at this. What's different? Oh, I've got a ring with 3 conjugated double bonds, alternating double, single, and that's benzene. I have a bromo group, and my favorite, the T-butyl group. So what do we have? And also it's 1, 2, 3 disubstituted. We have benzene. Actually, I'm doing that wrong. If you have it either way, I would mark it correct. The reason I did this is because R comes before U in the alphabet. And then 1, 3 would be meta. So that'd be meta-bromo, T-butyl, benzene. Say that 3 times quickly. And if you put the bromo and the T-butyl the other way, like I started to, that would be correct on the test, even though the IUPAC would arrest you. Let us know what IUPAC. not write this down, but does everybody know what that is? Oh, come on. It's paramedic. Who said organic things we can't do? Fun or get a crone out of a glass. And I got it on tape too. Ooh, that's something. All right, two types of nomenclature question. Here's the name, draw. Here's the structure, give the name. Here's the name, draw the structure. And if I were to put on a test, draw the structure for the following name. And the question would be, how do you do that? Always start from the right. First thing I see is benzene. Well, hopefully you've learned before next Thursday, this is a benzene ring. Then, if you look on the table here, what is iodo? It's an iodine. And you can put it on any carbon because it's this mono-substituted. Most of you will do here. You can put it here, 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 and you're done. I'm going to try something different. I'm going to let you try this one right now, because I haven't done an example with dye substitute, but I think you might have the hang. How to draw the structure for the following. And I have you look here, and also don't forget to look here. Remember, when you're done, look up and smile. All right, let's take a look at this. How do you decode this to know what to draw? You start at this end, the right, move that way. Ooh, benzene. 6-membered ring, 3 double bonds. You can also put a circle there. I just think this is a cool way of drawing it. Then I have an isopropyl group and a nitro group, and they're ortho. And it doesn't matter which one you put here or which carbon you start with, say, an isopropyl or a nitro, because you just do one carbon over and put the other one, because ortho, 1,2 dye substitute. Most of you will probably do this. Isopropyl, 3 carbons, center carbon. Next, nitro. And if I call this one, most of you are going to go clockwise, NO2. That's one way of drawing it. Here's another way. Benzene ring, isopropyl, nitro, 1, 2. All I've done is flip the ring. Remember, rings like my pen, like me, like you, are not stuck in one position. They move around. And that's how you do it. Question?
Does it matter which one you put as 1 or 2?
Which one what?
Does it matter, like if you put the nitro as 1 or the isopropyl as 2?
Oh,
or
it's
1?
relative to each other. So the top carbon on a benzene ring is not 1. You can make it 1. You can make any carbon. When I draw a benzene ring, look out, I'm having a good ring drawing day. That can be 1, that can be 1, that. If I make this 1, then where's 2? This carbon or that carbon?
What if you had 3, what if you had like nitro, nitro isopropyl, and then like a third, how do you know which
All right,
one goes
there.
in order?
I'm going to get to that next. I mean, in other words, if you have more than 2 groups.
Yeah.
Okay, let's do that. Then you don't use ortho, meta, and pair, then you use numbers.
Okay.
Because ortho, meta, and pair are only for di, substitute di, meaning 2. By the way, you still have to know how to count up to 10. So you all hopefully know 2. But let's try one. One thing I should point out, sometimes you'll see in my software too, write a nitro group this way, or you can also see it writing it this way. Either way, this is a nitro group like this nitro group like that nitro group. All right, question would be, what's the IUPAC name for that? And notice it has more than 2 substituents on it. When there are more than 2 substituents, you use numbers. Now, let's take a look at this one. And if I look at this, I say, ooh, methyl group on a benzene ring. What do we call that? Toluene. And in toluene, the methyl group is always 1. Next, I have a nitro group. Ooh, I have a second one. I have a third nitro group. 2 is di, 3 is tri. So this would be trinitro. Toluene. Now, if this is 1, going clockwise or counterclockwise, you'll get the same number. Notice, tri, you need 3 numbers. The nitro groups are on 2, 4, and 6. So this is 2, 4, 6, trinitrotoluene. Let's see, 2, 4, 6, trinitrotoluene. 2, 4, 6, trinitrotoluene. Oh, that's my jaw. 2, 4, 6, trinitro. Why don't we just give it a common name or a slang and call it TNT. 2,4,6 trinitrotoluene is the active ingredient in dynamite. I think you've all heard of TNT. How many of you have ever heard of the Nobel Prize? There are a bunch of them, one in chemistry, one in peace, one in medicine, and there are a couple others I'm forgetting, but those are the ones I can remember off the top of my head. And who started that? Alfred Nobel. Now, how did Alfred Nobel get all the money he made to set up the Nobel Prizes, which I think is a great thing? He and his brother found a way of stabilizing 2,4,6 trinitrotoluene. 2,4,6 trinitrotoluene is a liquid at room temperature. It's not this stuff. But if I had a bottle of this and I slammed it down real hard, this building wouldn't be here, we wouldn't be here. It's very, very shock sensitive. Well, how did he find out? He and his brother somehow found, if you mixed it with clay and diatomaceous earth, you could mold it into sticks. You found blasting caps you put in there which would set it off, and he came up with dynamite. And even then, when they made it, it was still dangerous. Unfortunately, his brother died when one of their plants blew up, sad. And there are various stories why he set up, but what you don't know, which I do, is where did most of the money or profits come from this invention? How to stabilize this, and he also was able to stabilize trinitroglycerin from military applications. In other words, armies used it for war. So all the Peace Prize and the other prizes come from profits that came mainly from sales to military for war applications. Is that good or bad? Not really. It's just life. Something you probably didn't know. See all the exciting things you're learning in my class. And I'll let you try. What's the IUPAC name for the following? Number 2 is die, 3 is try. Actually, that might not be the best example, but go ahead and do it anyways. No, actually, it would work. But this one's more in the gray area. All right, looks like everybody is just about done. All right, let's take a look at this. First of all, what do you see? Oh, a benzene ring. Then I have bromine, which is bromoethyl, second ethyl, diethyl. So this would be bromo. I'll put this up here because I run out of room there. And if I call the bromo group 1, this is 2, 3, 4, this would be 1 bromo and 2, actually 3, 4 diethyl. Now you could have called this 1, this 2, this 4, and I would accept that. So it'd be 4 bromo, 1, 2 diethyl. I'd probably go this way because the substituent with the highest alphabetical priority would get the lower number, and that's why this is not a good example. But it still gets you to understand to use number. And that's how you do nomenclature. Also, let me do one. I want to get into something before I run out of time today. I'll do more examples of this probably on Monday, but question is, how do you decode this to draw the structure? I'll do this because I want to get into something today. I'll do some more examples on Monday or maybe tomorrow. Toluene, benzene ring with a methyl group. Dichloro, 2 chlorines. Where are they in carbons 2 and 3? Remember, the toluene, the methyl group is 1. Therefore, I can go either clockwise or counterclockwise. Most of you are going to go clockwise. This is 2, this is 3. How do I put a chlorine on there? I do that, di is 2. And it turns out halogenated aromatics like benzene for a while have been, except until they found out they were quite hazardous to our health, certain herbicides like DDT and things like that are halogenated aromatics. Also, these were good molecules that were used for heat transfer, like your antifreeze, but not in antifreeze, but in the ballast for transformers. Here are those big ones you see the power companies using. All right, let's move on to the chemistry of benzene. I want to get through this today. I'm going to zoom through this because this is turn the switch, low on test, but off. All right, due to resonance energy, if you take a benzene ring and you calculate how much energy, cyclohexane ring and 3 double bonds, and you add that up, you can do that, and we won't do that in this class, you get a number. If you actually measure in the lab the energy of benzene, it's much lower, more stable. And that's because of the resonance these high electrons in double bond are holding hands. And benzene does not react like cyclohexane or a molecule of 3 separate double bonds. There's something different. And that's the resonance energy, or also known as stabilization. I'll never ask this on a test, and the ACS doesn't either. The difference between the calculated and the actual is what we call resonance energy, and aromatic compounds are much more stable, again, switches off position, than non-aromatic, like cyclohexane, double bond. And this is due to resonance energy, and it's a very important complex thing. Because of that, which is solely off position, benzene rings do not do addition reactions like double bond, where you break the pi bond and add something to 2 carbons. They don't do that. As soon as you break the pi bond, you lose all that resonance energy. It's not as stable, and therefore it says, I'm not going to do this. Actually, it doesn't say that, but this doesn't. And therefore, benzene, aromatic compounds, undergo a different type of chemical reaction, which we call electrophilic aromatic substitution. I'll never ask that on the test, but I'll use the terminology. Substitution means you replace one of the hydrogens on the benzene ring with something. And it's aromatic because we're dealing with a benzene ring. What's the term electrophile? Let's see, electrons, I know, that's a negative charge. And what does the word, or part of the word file mean? Lover. If somebody's an audiophile, they love music. There are other files which I won't talk about because we know that that's another story. But anyways, electrophile is a group that's looking for electrons. And if I'm an electrophile, I love electrons. Where can I find them? Well, the pi electrons on the benzene ring, remember the 2 clouds? This is going to attract and say, whoa, I'm an electrophile, I want to react with you, and they do. So let's look at the first reaction, and that's halogenation. Switch is on. If I take a benzene ring, or it turns out any aromatic compound, but for this class I'll just stick to benzene rings. You react it with halogen gas, where X for this is usually chlorine or bromine. It could be iodine, but I've never seen it. It's never seen it with fluorine. And what you do is you put a halogen on one of the carbons of the benzene ring. You replace one of the hydrogens. Now, here's something rare. You also get something inorganic, and Dr. White actually showed it on a slide. I'm putting it in quotes because you don't have to put that down in my test. You people in front have everybody behind you as witnesses. I said that because organic chemists are very biased when it comes to inorganic stuff. And why bother with it? Unless you're working in a plant and you got to clean it up. You're getting 2,000 pounds of that for on the board, thinking about it. And if we look at an example, what would be the product or products for the following? Ooh, what's different? Benzene ring. What am I reacting it with? Halogen and ferric, so I use the X. Ferric trichloride. You need the catalyst to react with the chlorine gas to make this reaction go quicker. And as a catalyst, it's not really consumed. And what happens? You get the benzene ring, because you don't break carbon-carbon single bonds. And in a benzene ring, you're never going to, almost never, break the pi bonds, 3 bonds, and replace one of the hydrogens, doesn't matter which one, mostly you're going to pick this one, and with the chlorine. Now, the only other reaction I could ask on a test is where that's a bromine, and you do the same thing with bromine and ferric tribromide. Why? And what I'm going to write on the board, you don't have to write down, but I just want to mention it. Now, if I'm going to do this halogenation, I'm going to put a halogen on a ring where I already have a group. For some reason, in organic chemistry, when you talk about this, they use the letter Z. Don't ask me why. This is called a director. Have you ever gone to a concert or a state county fair where they have this big open field or a parking lot with no lines on it? They have those people who do not like me, and I don't like them either. They tell you, no, don't park there, park down there, because we're trying to fill up the parking lot. Park there, they're directing where to park. I don't listen to them. So anyways, this is a director. The halogen coming in can go either to this ortho positions, can go to this meta positions, or to para. And it turns out there are 2 types of directors, which is in the off position. Ortho-para directors and meta, depending on what Z is. I will bet most of you will never do after this class or think about directors and electrophilic substitution. But after my class, you will think about proteins, you'll think about carbohydrates, and you'll probably think about fats and oils. Therefore, I'm not going to spend a week on this, which you'll probably forget and have difficulties. We'll do one in the lab, though. What directors are. Therefore, in my test, I'm going to stick to only using benzene, so I'm done with this reaction. Because the only one I can do is bromine. Next reaction I'd like to talk about is nitration. And nitration, putting a nitro group, like you saw in TNT, trinitrotoluene. How do they put the nitro groups on a benzene ring? Because you can't go out and Mother Nature doesn't make that. You do nitration. And nitration is where you react nitric acid, HNO3, and sulfuric acid, H2SO4, with a benzene ring. And this gives a nitro group. Notice here, HNO3, nitro group is NO2, not NO3. What I'm going to write on the board will never be on my test. You think of nitric acid as an acid, a proton donor, H+. Sulfuric acid is a proton donor, and I have nitric acid, which I'm going to draw this way. Oh, look. Oxygen with non-bonding electrons. This will go do this. Again, this won't be on a test. And you form this positively charged intermediate. Whenever you can lose a good, stable molecule from a bigger molecule, it says, I'm out of here. Anybody see something familiar? 2 hydrogens and an oxygen? Water. And what happens is you lose water and you form the nitronium ion, which is an electrophile, because it says, I don't want this positive charge. Where there are some electrons, and it says, ooh, benzene ring, and that's how you get the NO2 from this and this. This is the only reaction I can ask on the test, so I can't ask any more. And it looks like I'll let you out a whole 2 seconds early. For those of you who have lab tomorrow, don't forget to bring your lab here. Handing in as you did last week.